Now that we have gone through and seen the story about the 1 grain of rice, we can now think about how that relates to some of the work that we've been doing related to exponents and exponential growth. So at the beginning of the unit, we had talked about a similar story with if your mom gives you 1 penny for an allowance, but then decides to double your allowance every day for a year, so that you'd have 2 pennies on the next day. On the third day, you had 4 pennies and then 8 pennies. Would that be a good deal? And we recalled from that story that by the end of the year, you essentially had more money than the entire United States could ever produce in a particular year. So the amount of growth in that money was very, very substantial and exponential, especially as you got to the end of the year. So with the grain of rice, we have a similar situation. We start with 1. So we start with 1 grain of rice, and then we keep multiplying by 2. In other words, we keep doubling that number of grains. Now, if you take a cup full of rice at home and you start counting the grains, there are a lot of grains in even 1 cup of rice. So it would take a long time, you would think, for the amount of rice, even doubling 2 grains, 4 grains, 8 grains, to get big enough to worry about. But we see that with exponential growth, some unexpected things start to happen. So if we expand out that situation, think about starting with 1 and then double it. So multiply by 2 again, multiply by 2 again, and again and again, and so on and so on. We have basically that mathematical statement. You can see this kind of like an expanded form problem. So we start off with 1 really. Use a different color here. We're going to start off at 1, and then we double it, and then we multiply 2 by itself a certain amount of times. Now up here I have, let's see, 1, 2, 3, 4, 5 times, so it could be 1 times 2 to the 5th to represent what I wrote down here. But this statement right here represents for any amount of times that I'm doubling 2, how many grains of rice will I have? And this is what we call our exponential form here. So when we write an exponential equation, it looks kind of like this up here. It looks like that. It also looks kind of like a linear equation in some way. So an exponential equation is y equals a times b to the power of x. Now, remember when we did linear equations, we had y equals mx plus b. Sometimes people write it as a plus bx, or y equals ax plus b. Use different variables, essentially, for the y-intercept and the slope. Well, if we write it this way for our exponential equation, this right here is going to be our y-intercept. That's going to be our starting amount. So to speak. Okay? So it's the y-intercept, or our starting amount. And so just like a linear equation, like if we wrote it this way over here, a would be the y-intercept value. And then instead of having a slope like we do with a linear equation, we have a growth or decay factor. Sometimes that's referred to as the multiplier, because that's essentially what we're doing is we're multiplying. And so if our exponential situation has growth, then this right here will be bigger than 1. If it has a decay, if something is decaying, then essentially it's decreasing. That's what that means. Then that would be, well, less than 1, I would say between 0 and 1. So like 3/4 or 0.75 would be a decay factor, or 0.25 would be a decay factor, or 0.13, 1300ths would be a decay factor. So between 0 and 1 would be a decay factor. Okay? So that's what we have to be thinking about when we are thinking about our exponential equations. So if we look at a table of values over here and look at what our y-intercept would be and what our growth and decay factor would be, remember the y-intercept always has an x value of 0. So if we look on the table here, when we have an x value of 0, the y value is 4. So the y-intercept is 4. The growth or decay factor would be then, okay, well, what are we multiplying by to get from 1 to the next, to the next, to the next? So 4, 8, 16. Notice we're not adding 4 every time. We're adding 4 here, let's say, but then the next one would be 12. So we know it's not a linear problem, not a linear equation, because we're not adding the same amount each time, but we are multiplying. You'll probably notice that we're multiplying by 2 each time. Okay? So that is our growth factor in this case, because it's bigger than 1, so we are growing. You can see that the y values are growing here, getting bigger. So then our equation will be y equals our y-intercept of 4 times our growth factor to the power of x. So 4 times 2 to the power of x. So if I want to figure out, okay, what would be the y value when x is 5, either I'd continue to double it here, which I could probably do in my head. That's possible. But if it were like 50, that would be a long period or a long list of numbers there to be able to do it. So we want to use our equation here and plug in that value of x. So if x is 5, we're going to do 4 times 2 to the power of 5. And at this point, you could probably punch it in on your calculator. I mean, essentially you've got 4 times 2 to the power of 5 is 32. So 4 times 32 is going to be 128. But the y value there, what we probably want to do is just type into your calculator 4 times 2 to the power of 5, and you will get that number. Usually we do need our calculators for exponential growth because the numbers get very, very big, or if they're decaying, they become decimals. So that is a thing that we have to consider, a factor we have to consider. Looking at number 2 here, notice that across from 0 is 8, so our y-intercept is 8. And notice it is growing, so we have a growth factor. But the question is, what are we multiplying by here to get from 8 to 12, from 12 to 18, from 18 to 27? So over here, it was pretty easy to tell that this was multiplying by 2, and maybe some of you guys can see what this growth factor is. Once you've identified that it's probably a growth factor, what you can do is you can take any 2 consecutive numbers, as long as the x values are increasing by the same amount. And to get the growth factor, we will take and divide the second number by the first number, so 12 divided by 8. And when you do that, you'll see that your growth factor is 1.5. Now, just to demonstrate, that could happen between any 2 numbers. I mean, you could take 18 divided by 12 is also 1.5, and 27 divided by 18 is also 1.5. And we need that to be true, right? Because we need to have the same multiplier, the same growth factor between every set of y values as the x values increase by the same amount as well. So if you're not sure of the growth factor, you can always take the second one divided by the first one to get that growth factor. Like 8 divided by 4 is 2, 16 divided by 8 is 2. We could do this one in our head, but sometimes it is more challenging. So our equation then is y equals 8 times 1.5 to the power of x. And so if we're plugging this in, 8 times 1.5 to the power of 5, then we'll have to go over to our calculator on that one. And I am going to do so as well off screen here. And that gives us a total of 60.75. 8 times 1.5 to the power of 5 is 60.75. Okay? So you can see that exponential problems usually require you to maybe dig in with your calculator a little bit because the numbers are a little bit hard to calculate in your head as you get through some of these problems. All right, so next one, we have a y-intercept value of 64 and growth or decay factor. Okay, so notice what's happening here, that we are actually decaying, so we're decreasing. And then the question is what? Well, if you look carefully here, you can see we're kind of dividing by 4. But what I want is a multiplier here. I want a multiplier. And so when you divide by 4, that's the same thing as multiplying by, well, let's just take second divided by the first. So 16 divided by 64. So decay factor. 16 divided by 64 will be 1/4, which is the same as a decimal 25/100ths or 0.25. So 4 divided by 16, you'll notice we get that same decay factor. 1 divided by 4, it's also 0.25. So if we're dividing by 4, it would make sense that that's the same thing as multiplying by 1/4, which is the same thing as the decimal 25/100ths or 0.25, as some people will say. All right, so equation will be y equals 64 times the decay factor of 0.25 to the power of x. And so if we're then plugging in another x value of 5, okay, so 64 times 0.25 to the power of 5, we get a total of 0.0625. So this is decaying very close to 0, actually. And a decay factor is something that I was recently kind of talking about when you have to take a prescription for medication or something. All those prescriptions, those drugs that are in your system, have a decay factor. And the different drugs have different decay factors. So there's something called a half-life. And basically it is how long it takes before half of the drug remains in your system. And this can apply to different situations. But that's important to know because you need to know how long it will have to be before you take another dose of that medication. And it all depends on what the half-life is. Because if the half-life is short, then you're going to take that medication more quickly to get it back to where it's supposed to be in your system. If it's long, you're going to wait a little while. Otherwise, if you take too many in a short period of time, now you have too much medication in your system. So that decay factor is very, very critical, actually, to people being healthy when they're taking medications.